All right, good morning. So the first talk of this session will be an invited talk by John Baez of UC Riverside. John is an accomplished mathematical physicist, and in recent years he's been applying work on networks to climate science, and this is what he'll be talking about today. So without further ado, John.
Thanks. I have no idea how to put this thing on. Should I put this on? Okay, well then I'm sort of trapped. I'd like to run around. Sorry.
Testing.
You hear it? Sorry. Stuff.
Should you pause your belt?
Yeah.
Turn up the volume of the board.
Okay, great. Sure. Hi. So I'd like to speak about networks in climate science. All the work that I'm going to talk about has been, well, some of it's by other teams, but all the work that I've done has been in cooperation with this friendly gang of people that we call the Azimuth Project. All these people listed on the bottom there. The idea is that I got really interested in environmental issues. I guess worried is more the right word than interested. And so I decided to switch from my work on abstruse things like category theory and quantum gravity towards something a bit more practical, and decided to start up a kind of organization where people could just join, and people whose jobs might be in industry, for example, in statistics or computer programming or whatever they want, join in and help tackle some environmental issues. And so we've been working on that for about 4 years, and this is one of the first projects that we've managed to carry out. So I'll tell you about it. So it's largely going to be concerned about this El Nino, or what's called the El Nino Southern Oscillation. So if you look at the Earth's temperature, the main thing you notice over the last 100 years, this graph starts from 1950, but you could go back further, is that it's going up. This is the Earth's average global temperature measured from some more or less arbitrary baseline. So that's global warming, and that's why I got interested in climate science in the first place. It's going to be one of the key challenges of this century to transform our civilization to one that basically puts out almost essentially no carbon dioxide, whereas right now, of course, all of our industrial civilization is based on burning carbon. So it's going to be an amazing transformation if we succeed at all. And one of the many things we need to do is to better understand the relationship between carbon emissions and climate. And if you look at this graph, you'll notice that it's by no means a smooth curve. There's a lot of natural variability in the Earth's temperature, lots of wiggles on top of the trend, and understanding those is important for a lot of reasons. And one of the main causes is this El Nino. You'll see that certain years marked in red when an El Nino occurs tend to be hotter than average. There's an opposite situation called a La Nina, when the Earth tends to be cooler than average, and then there are intermediate years marked in gray. Well, what is El Nino exactly? The last really big El Nino happened around 1997, and it affected things worldwide. It's centered in the Pacific Ocean, but it strongly affects the land masses surrounding the Pacific and even further out. The fact that this nice little map was put out by an organization called Shrimp News International suggests a little bit about how widespread the effects of El Nino are. Shrimp farmers are affected by it. All sorts of farmers are affected by it. It causes billions of dollars in economic damages due to droughts some places, floods other places, and being able to predict it would be a really great thing. I want to switch for a second. This is not going to be as easy as I expected, because this sorry, because the screen is narrowed from how I used to see it. I think I won't switch. I wanted to show you a little animation of what goes on, but I guess I'll just act it out in words. So it's all about the Pacific Ocean in its central aspect. So wind blows across the Pacific Ocean generally from California over towards Asia, and that means that hot water on the surface of the Pacific, sitting there out in the sun near the equator, gets pushed over towards Asia. It builds up. When it builds up, that's a La Nina condition, when it's all over there near Asia. But then, for some not completely understood reason, sometimes the winds will slacken off, and that hot water will start drifting back towards California, towards the Americas, and you wind up getting a big pool of warmer than average water in that part of the Pacific Ocean. That's an El Nino. Somehow that process also brings up a lot of stored heat from the depths of the ocean to the surface. And what happens, of course, is the warm water evaporates, so it brings up the latent heat of the water into the atmosphere, and the whole Earth winds up warming up. You also get floods and a lot of rain in that side of the Pacific Ocean when that happens. It's a very complex process. It also involves what's going on under the water. There's a cold bottom layer of the ocean and a warm upper layer, and there are actually waves between the upper layer and the bottom layer, and the waves move very slowly because the density difference is low, and those waves actually take months or almost a year to cross the Pacific Ocean, and they're quite significant, and that's also part of this oscillation process, these underwater waves. This whole process takes about 4 to 7 years. That is, every El Niños occur in a non-periodic cycle of between 4 and 7 years. There are 2 signs of an El Nino that people use to diagnose the condition, although there are many different coupled things going on. So one of them is increased sea surface temperatures in a certain patch of the Pacific that's been somewhat arbitrarily picked out and called the Nino 3.4 region. So people measure the temperature anomaly in this region. I'll be using the phrase temperature anomaly a lot, and that just simply means the temperature at some given time minus the historical average temperature during that time of year. So working with the temperature anomaly is a way of subtracting out the seasonal variations in temperature, which are huge but not incredibly interesting, and focusing on the changes from year to year. So the temperature anomaly in this region is called the Nino 3.4 index, and when it gets above 0.5 degrees Celsius, half a degree Celsius, then we're getting into El Nino territory, although I'll give you the precise definition of an El Nino later. But it's about that El Nino, that Nino 3.4 index. A second thing that's been observed for a long time is that when this happens, the air pressure in the western side of the Pacific Ocean decreases compared to that on the eastern side. And this difference, or more precisely the difference in pressure anomalies, is called the Southern Oscillation Index. So there are these 2 things worth keeping an eye on, and they're very strongly anti-correlated. Here are graphs of the Nino 3.4 index on top, and the Southern Oscillation Index down below, and you can see that one of them looks almost like an upside-down version of the other. For some silly reason, people decided to take the air pressure at Darwin and subtract the pressure at Tahiti and subtract the temperature at Darwin instead of the other way around. That's a purely arbitrary decision, and so that's why the second graph looks like an upside-down version of the first one. If they'd been more smart, maybe they would have done the subtraction in the other order, and then we wouldn't have to worry about that silly minus sign. But the main point is that these are strongly correlated variables, one having to do with air pressure, the other having to do with temperature. And you can see also from this graph the irregularity of the process. There's some kind of thing going on, some kind of peak roughly every 4 to 7 years, but some peaks are big, some are small. It's by no means anything like a sine wave. So it's a complex phenomenon. So it's just one of many such phenomena called teleconnections. So I may slip into using the jargon ENSO for this oscillation, the El Nino Southern Oscillation, but there are a lot of other teleconnections that all have their own obscure acronyms, which I won't bother you with. And what they are is there's strong correlations between weather at distant locations on the Earth, say more than 1,000 kilometers apart. And people have systematically been looking for them. We saw a great tutorial on machine learning in climate science on Monday, and there we saw recent attempts to look for those very systematically just by throwing a bunch of data into a machine and running the right kind of program to look for it. But before that, weather experts had been sort of less objectively looking for them, and they basically found most of the same ones. So if you do, in some earlier versions, you would do principal component analysis on the temperature field of the Earth, and you'd find these different patterns, these different teleconnections. And the thing to keep in mind for now is that the El Nino Southern Oscillation is the biggest one of them on time scales that are between a year and a decade. There's some others that can take many decades, like the Atlantic multi-decadal oscillation. There's some that seem to take so long that our historical records are just barely long enough to see one or two of the oscillations. Those are a bit frustrating. But we've seen lots of El Nino Southern Oscillations, and recently paleoclimate data has shown that those have been going on for many thousands of years earlier. So a new look at this is given by what's called, a bit pompously, I must admit, complex network theory. So this is really what I would call applied graph theory. It's the study of really large graphs that you can find in natural and social processes. And it's become popular partially just because it's a lot easier to get a hold of the data and process it these days. So bottom here, for example, is an enormous graph formed by taking, I believe, maybe the 20,000 biggest companies in the world and connecting an edge from one over to the other if one of them owns stock in the other. They all own stock in each other, roughly speaking, but you can notice some interesting things about this graph. In particular, as typical for these graphs, there's a hub, a bunch of nodes that are connected to lots of other nodes. Often you might have to go through the hub to get from one node to any other node. And not surprisingly, in this particular case, that hub consists of major financial institutions, which sort of rule the world now, I'm sure you've noticed, and which all own shares in each other. And so this is an example of objectively studying this interesting phenomenon of how corporations control each other. So the basic idea of complex network theory is not at all complex. It's very simple. You start with a weighted graph. So for me, that will be some set of nodes or vertices. And then for any pair of nodes, a number, a non-negative number, called the weight, Aij. And there's no reason for Aij to equal Aji, although sometimes that will occur. So sometimes this is too much for people to handle, so they'll turn this weighted graph into just a plain old graph by drawing an edge from I to j whenever this weight, Aij, exceeds some threshold, some number c that you get to pick. So that's a way of picking out only the strongest connections. So you think of the weight as how strongly connected something is to something else, and you can make this graph where you keep only the strongest connections, often called links. So the general idea of complex network theory is to take some situation you're interested in, construct a huge weighted graph from it, and then use different methods to calculate quantities from that weighted graph, and try to learn something interesting. I'd say that this is very much we're very much in the early stage of this science. People are writing lots of papers where they take one of the hundreds of different quantities that people have thought of calculating, and they'll calculate it, or a bunch of them, for the weighted graph that they're interested in, and they'll point out things that are interesting about that. Since I come from a tradition of a very old science, namely mathematical physics, where you actually write down differential equations that can predict what's going to happen and things like that, this seems very exploratory to me, much more like going out into the jungle and collecting samples of different interesting species, and then later on hoping that some Darwin will come along and make sense of it all. But that's great. So I'm going to focus on the simplest possible thing that you can calculate from a weighted graph, because I don't want to astound you with my knowledge of all the crazy things you can calculate. So the simplest thing is the degree of a node. And because this graph, these weights are not symmetrical, Aij is not the same as Aji, we have to be a little careful here. So we'll pick a node j, and then we'll sum Aij over all other nodes I. We could think of that as how much interest all those other nodes have in this node. So for example, if we let Aij be the number of web pages I that link to the specific web page j, then a web page with a high in degree will be one that a lot of people are linking to. And if you do this type of analysis, of course, you can find web pages that are in some sense important or interesting. Or similarly, if a lot of people like you on Facebook, you will have a high in degree. So you're officially important. So we could try to do that kind of thing with climate data. So in a paper called Complex Networks in Climate Dynamics, some authors, Donges et al., what they did was they took daily surface air temperatures on a grid, and I actually should mean temperature anomalies, but I'll get to that. And so these data are luckily easy to get. You can download huge amounts of data about daily temperatures on a grid over the whole Earth from NOAA and other government agencies around the world. But unfortunately, for some reason, these folks decided to take data using a climate model. I have no idea why, because the real world data is there, and it would probably give similar results, but oh well. And what they did is they computed for each pair of grid points the correlation between the daily surface air temperatures. So more precisely what they did is for each grid point I, they took the temperature T sub I, which is a function of time, say month, and they computed the linear or Pearson correlation of those variables, which is just the mean of the product divided by the product of the standard deviations, because the means of these variables Ti are 0, because they're defined as anomalies. They're defined by subtracting off a mean. So this is just the simplest kind of linear correlation between variables, and it's been normalized so that it ranges between -1 and 1. Everyone should know about this. It's symmetrical, so it gives no information about who's making who do something. It's just correlation, linear correlation. Then what they did is they created a graph where there's an edge between the ith node and the jth node when the absolute value of this correlation exceeds some threshold. They take the absolute value because you might have two points that are anti-correlated, but that's still some kind of a important relationship between them. How do you pick the threshold? Well, there's no particular way that's obviously best, but obviously if you pick the threshold too low, everyone will be connected to everyone else and you get no information. And if the threshold's too high, almost no one's connected to nobody else, and so you also don't get much information. So they just adjusted the threshold so that 0.5% of the pairs of these climate sites had an edge between them, and they said that the results are fairly robust with respect to varying that a little bit. And so the interesting thing is to see what they actually get. So this is the map they get. What they did is they plotted the degree of each node, so the number of other locations on the Earth that are highly correlated in their temperature to that one. And to be precise, they weighted this degree by the area of its grid square, because as you probably know, Greenland is not almost as big as Australia. It just looks that way because the Mercator projection. And so similarly, grid squares are a little bit misleading near the North Pole. So you should multiply the degree by the area of the grid square to be more fair. And what you see is this amazing thing that a certain patch of the Earth dominates the world, and that's what people had already called the El Nino Basin. It's this region of the Pacific which gets hot near the American side when we're in an El Nino condition, and it gets hot in the Asian side, we're in a La Nina condition. And they're very interesting patterns of blobs of hot water that drift across the Pacific as we're going from one condition to another. And as I said, the El Nino or La Nina affects the weather worldwide. So this is the kind of hub of the social network of climate. These would be the Tom Cruises and Angelina Jolies of the Earth's climate, if the climate were Facebook. So these very reddest patches are nodes that are connected to 5% or more of the other nodes, which means 10 times as many as average. So that's a nice sort of objective indication that El Nino is a real thing. But you could ask, is this just because we're only looking at linear correlations? The Earth's climate is some complicated nonlinear system. Isn't it bad to just be using Pearson or linear correlation to detect the relationship between temperatures at different points? Well, you could repeat the procedure using some other measure, and don't just did that for mutual information, which is very nice because it's invariant under a lot of transformations, and they find basically the same pattern. So what that means is that linear correlation isn't so bad for understanding correlation, at least at this level of detail. And that's not actually so surprising because the simplest weather phenomenon is that it gets hot somewhere and then it makes it hot somewhere else or cold somewhere else. It's some complicated functional relationship isn't the main point. You can also look at how these climate networks change with time. So there's a paper, Topology and Predictability of El Nino and La Nina Networks by Tsonis and Swanson, who created a climate network in a way that's pretty similar to the one I just described. The main differences are, first of all, they actually use real data instead of a climate model. Hooray! So they used actual temperature data from 1950 to 2005. More importantly, in the grand scheme of things, they separately created climate networks during two time periods. The El Nino period, certain times which are officially designated El Ninos, and La Ninas, and not the times in between. There are these intermediate times, which are actually most of the times. They created a link between the grid points when their correlation, defined just as I gave you in the formula, is greater than some amount. The absolute value is greater than 0.5. And they also only use temperature data from November and March. We're subtracting out the seasonal temperature change, but they claim that the summer is still distracting. It still exerts confounding influences. And so here's what they get. This is their map for the La Nina conditions. So the brightness here is the fraction of the total area of the Earth to which a given grid point is connected. So we see the El Nino Basin there in the middle of the Pacific Ocean near the equator. We also see other patches. Basically, mostly, they're patches of large ocean near the equator. That's where the Earth soaks up most of its energy from the sun, which then gets distributed around the world by means of weather, and then eventually, of course, radiated out into space. So it's not surprising that those are the main places, the places that are where the temperature is most strongly correlated to the temperatures elsewhere. So that's La Nina. What about El Nino? Here's the same map for El Nino. So it's qualitatively similar, but the main thing you see is that it's weaker. there are fewer strong correlations between different locations during an El Nino condition. So they summarize that by saying that El Nino breaks climate links. So when I first saw this, I was a little surprised because we seem to have some paradox going on here, which is not really a paradox. But so we see that on the one hand, the El Nino basin is the region in the Earth that's the most strongly correlated to all the rest. But on the other hand, when an El Nino is actually occurring, the correlation is less. Those are not really in conflict. You could say that the El Nino is like the bull in the china shop that disrupts correlations between weather worldwide. But it's an interesting pair of facts. So can we use this for anything? Can we actually try to predict El Ninos using climate networks? We'd love to do it because they have huge effects on agriculture. As I mentioned, they can cause billions of dollars in economic consequences. But it's very hard to predict them more than 6 months in advance. People aren't even completely sure why. There are two main theories that could both be true. One is that the El Nino system inherently is chaotic, so its self-contained dynamics is hard to predict. You have divergent trajectories in the dynamical system. The other is that it's affected by noise from outside. Phenomena from outside are affecting it in a significant way, stochastically. There are papers arguing both sides of that debate, and quite possibly, of course, the answer is that they're both somewhat true, and we need to get more quantitative to figure out. But what we know is that nobody's good at predicting El Ninos. So what would we like to predict? Well, the official definition of an El Nino is that the 3-month running average of this Nino 3.4 index exceeds half a degree for a period of 5 months. Rather complicated clause there, but that's what people call an El Nino. Of course, the simpler quantity is just the Nino 3.4 index itself, the temperature anomaly in this patch of the Pacific, and there are lots of teams trying to predict that. There's a nice website where you can see the latest news, and so this is the ast one that I was able to get. Came out in mid-November. Maybe another one has come out just yesterday. I didn't check. But you can see that there are a lot of teams. The teams on top are using dynamical models, detailed models of the physics. The teams on bottom are using statistical models, machine learning, Markov models, and so on. And the very interesting thing for you guys, I think, is that right now the two approaches are running neck and neck. In other words, the system is so complicated that even detailed, or it's so chaotic or so random or so something or other that even detailed physical models aren't actually able to consistently beat machine learning methods. So as you can see, the predictions are all over the place. As I mentioned, the definition of El Nino involves this index going over 0.5 for long enough. So you can see that we are coming up to 1, perhaps, but there's disagreement between the different models about which is whether we're going to have one or not. And so the U.S. government puts out a consensus average, and that actually is known to do better than any one of the models. So there's a paper by Ludescher et al. Called Very Early Warning of Next El Nino, which tried to use climate network methods to predict El Ninos. So what they did is they built a climate network by using correlations in daily surface air temperatures between points inside the El Nino basin, which are these red dots here, and some points outside the region, the other dots, so a big rectangle around the Pacific. And they used these correlations to construct a weighted graph, and roughly they predict an El Nino will occur if the average weight between points exceeds a certain threshold. I think I'll run you through what they do. I think it's a bit too Baroque. I would love to simplify it, and I will eventually, but here's what they do. So they start with these surface air temperature anomalies at the ith grid point at time t. They look at time-delayed versions of covariance, that is the temperature Ti of t times the temperature at another location j at some shifted time, t minus tau, take the mean of the product minus the product of the means, where these means are only over the last year. They're running averages because we want to see how this quantity itself, this covariance, changes with time. They get to adjust this parameter tau, this time delay. So that's how much things here are correlated to here at some other time, shifted by tau. So then they take that quantity and they normalize it to get a quantity that goes from -1 to 1. It's a kind of correlation. So it's the correlation at time t, that's the superscript between locations I and j with lag tau. Okay, that's not done, unfortunately. Then for any pair of nodes, they figure out the biggest that gets, the average, and the standard deviation as this delay ranges from 200 to -200 days. And finally, to get their weighted graph, or almost finally, they define the length strength to be the difference between the maximum of that and the mean of that, normalized, dividing by its standard deviation. So this is quite elaborate, but it's basically saying how much the correlation between these 2 points, allowing for all sorts of, allowing for a lag, tau, can become bigger than its average. How much it's able to shoot above its average. And then they just average that over all pairs where one point I is inside the El Nino basin and the other point J is outside the basin in that larger rectangle. So it's the average connection between climate in the, or weather, temperature in the basin and outside, allowing for all sorts of lagged correlations. So this is what they get. Well, so this is a sort of complicated graph. The blue stuff is not what the red line is what they get from the complicated formula I just described. The blue stuff is basically the Nino 3.4 index, but we're only drawing it when it gets above 0.5 degrees. So those blue peaks are potential El Ninos. They're times when the Nino 3.4 index is high. The red stuff, the red line, that's this average length strength that I just explained to you rather laboriously. And so their method of prediction is that when that red line exceeds a certain threshold, which they've chosen cleverly, and that's the horizontal line in the graph, then they predict that if the Nino 3.4 index isn't already over 0.5 degrees, that then it will get to be over 0.5 degrees in the next calendar year. So you'll notice that sometimes it works and sometimes it doesn't. Sometimes there'll be a red peak there and then a blue peak afterwards. These green arrows are indicating, yes, we succeeded. I see at least one dashed black arrow, which is no, we didn't succeed. So they chose this threshold by training their algorithm on climate data for one chunk of time, and then they tested this method on data for a more recent chunk of time. And with this threshold, they claimed that their El Nino predictions were right 76% of the time. That is, when they say there's going to be an El Nino next year, according to their definition, which is just that the Nino 3.4 goes over a half degree sometime. That's not the official definition. That they're right about 3/4 of the time. When they say there's not going to be an El Nino, they're right 86% of the time. So what got people interested in this paper is that they actually stuck their neck out. That this paper came out in February of this year. It was written in December of last year, and they claimed that that the Nino 3.4 index would actually exceed half a degree by the end of this year with a 3/4 probability. So in other words, their conditions for a prediction were met, and so they said, yes, it's going to happen. And just last week, the latest data says, yes, it's happened. So the Nino 3.4 had been edging up to 0.5 above average, and in the latest official government report, it said, yes, it happened, and it will probably continue to go up for December. So they win. So the question is, how much does any of this mean? And what does it mean? So me and my pals at the Azimuth Project decided to look into this as a kind of way to do open science where we take a paper and we analyze it in more detail than the authors probably ever wanted anyone to analyze it. So we wrote code implementing their algorithm. The data they used is publicly available. So if we understood what they were saying in the paper, we should get exactly the same average link strength as theirs. We do not, but it's very close. So we don't know yet what the difference is. It doesn't seem to be extremely significant, but it's just, of course, annoying, at least to me. But that's not the most important thing. So the most important thing is to study their method. Well, it's important because if we got something dramatically different, then of course that would be very important. So Steve Venner, a statistician that is on our team, he did an analysis, and he estimated that the mean success probability, that is the probability in which their predictions are right, is 80% using their method. But he also noted that if you just always said there's not going to be an El Nino every year, you'd get a 71% success rate. So this is quite a lot of work for just a little improvement. He noted that their method has a 61% chance of predicting an El Nino initiation. That's what I'll use this. That term means that Nino 3.4 goes over 0.5 degrees. So this has a 60% of chance of having predicted it when it actually happens. That's a Bayesian type calculation, and he picks a certain prior for that. But that figure of 61% is floppy. That is, if you look at the 95% confidence interval, it's anywhere from about 40% to 80%. So this makes us wonder, how much does this average link strength really say about whether an El Nino is coming? There's a big problem of small sample size. So they only made a single yes or no prediction once each year for 65 years. And of course, they trained their algorithm on some of the data. So 31 of those years were used for training their method, leaving just 34 predictions, most of which are actually retradictions or hindcasts, and one actual prediction. So we need to think about things in different ways if we're going to understand if this method is really getting somewhere. And it turns out that some very simple ideas are interesting. So Daniel Mahler and Dara Scheide, who work on machine learning, they started by looking at some very simple things, some linear regressions, and then compared them to more complex things. So if we just plot Nino 3.4, that's what we're trying to predict, as a function of average link strength at the same moment in time, so not predictive at all, you get a very low R squared of 1.75%. So very roughly speaking, that means that knowing the average link strength today just explains 1.75% of the variance of the Nino 3.4 index today. In other words, these dots don't lie on a line. But that's not really the main point. We're not trying to use Nino 3.4 to predict we're not trying to use average link strength to predict Nino 3.4 today. We're trying to predict it in the future. So if we do that, if we use it to predict the Nino 3.4 6 months in the future, it's interesting that the R squared, while still pathetically low, 8.8%, it's higher. So there is some kind of sense in which knowing the average link strength today tells you more about the Nino 3.4 in the future than it does now. There are enough data points that all of these are extremely significant figures. They're very pathetic R squareds, but they're real. Okay, the numbers aren't just there by chance. Now, if we could try to do something simpler, just use the Nino 3.4 to predict itself in the future. The simplest way to predict something is to know it now and guess it'll be exactly the same in the future. That's how we operate in daily life most of the time, in fact. And that actually does better. That does as an R squared of 0.162. So this is not looking so good for average link strength. But here's something somewhat interesting, that if you look at Nino 3.4 as a function of average length strength and Nino 3.4 6 months earlier. That is, you combine the two methods, the dumb, obvious method and the length strength method, you improve your R squared to 0.22. So it's still bad, but you have to realize that all methods of predicting El Niños are bad. And this is far simpler than most of them, actually. So I'll compare some more complicated ones later, and you'll see that they are not much better. So just to summarize what I said and then move on, so if we think of this R squared as saying how much does knowing this account for the variance of that, then knowing the average length strength on a given month accounts for 8% of the variance of the Nino 3.4 index 6 months in the future. The Nino 3.4 index explains 16% of its own variance 6 months into the future. Taken together, you get 22%. What's interesting about that is that that's almost the sum of 22 is almost the sum of 8 and 16. In other words, it's largely independent information about the future, which knowing the Nino 3.4 now and knowing the average length strength now are giving you. So if that sum was 16% instead of 22%, you'd be learning nothing new from average length strength, but that's not the case. And what's interesting is that while this sounds pretty lousy, it's actually surprisingly good for a model that just keeps track of two variables. For example, Mahler did some more complicated things. So he used a random forest method called extra trees regressor to predict Nino 3.4 6 months in the future from a lot more data. So he got R squared equals just 0.23. So basically no better than knowing than this very simple method. Using air pressures got quite a bit better, but still not dramatically better. So it seems that there really is some concisely compressed information in this average length strength, although certainly not enough to really let us confidently predict El Niños by any means. And if you look at the correlation between the average length strength and the Nino 3.4 index, you notice something interesting, which is that the peak does not occur when the times are the same. These lines here are monthly intervals, and this peak at negative 10 months means that if you knew the length strength 10 months ago, that's when it would tell you the most about the Nino 3.4 today. So it really does have some futuristic quality to it, some future information quality to it. So my conclusion is that something like average length strength, some property describing correlations between weather in the El Nino basin and weather in the surrounding areas of the Pacific, really does have some predictive power for El Niños. But what is this quantity exactly and why? See, so far we've looked at one quantity, this rather convolutedly defined average length strength, and it does something. But maybe we could tweak it and make something that worked better. We don't really know why in detail to use one formula rather than the other. So we need to explore that issue. And so I think there's a lot of room for all of you folks who are good at machine learning to do things that are much more clever than any of the things that I've described here, and hopefully do better. And you can join this El Nino prediction contest and maybe try to beat the pants off the competition. So thanks.
All right, questions? All right, I'll start off with a question. So can these methods be used to predict climate at different temporal and spatial scales? For example, a country rather than the entire world, and maybe days instead of years and months?
I don't think anyone has tried that. People have only looked at these large-scale global phenomena. So in the tutorial, we heard some nice things about climate downscaling. So a lot of global climate models talk about what's going on very large scales and are not the best for predicting things locally, but there's really interesting work being done on trying to squeeze the local information out of that global information. You can just talk loud, I guess. Sorry. Uh-huh. To keep that information and then try to do machine learning techniques to predict? Exactly. No, they didn't try that, but we're going... Repeat the question. Yeah, so the question was, instead of trying to make the predictions based on this average length strength, where you're averaging some number over all pairs of points, could you just take that large matrix of all those lengths strengths between points and use that to predict, together with some machine learning method, to predict El Niños? And the answer is no, we haven't tried that, and they didn't try that. We're now in a position to try that because we have software that's freely available and files of all those length strengths.
Thank you.
Yep.
So could you say more about what the practical benefits would be of being able to predict El Niño more accurately?
Yeah, I'm not so strong on agriculture, but El Niño has really powerful impacts on rainfall especially in the Pacific Basin, and I gather that the farmers would love to know what the rainfall is going to be like ahead of time, so that they know stuff about what crops to plant. And so the fact that we can't give them predictions that are any good more than 6 months in advance really limits the benefit. Of course, being told that it's going to, for very short terms, weather forecasts are great, but for planting crops, you want longer term forecasts.
Hi, I guess my question is, sorry, similar to the question before. So it seems very nice. There's a lot of data to say whether you can predict this variable, but the question I have is about the validity of this variable. Do we have a lot of data about whether Nino 3.4 predicts anything really interesting except for the temperature in that patch of ocean?
I haven't seen detailed studies trying to validate Nino 3.4. There are other measures that people use besides Nino 3.4. For example, different patches of ocean, but also more complicated combinations of data. And there are discussions about which ones of those are better. So I would have to do some study to see in how much detail people have really tried to prove that one is better in some really precise sense. I suspect there's probably a lot of room for more work in that area as well. Yeah, I think people have, to a large extent, settled on this one variable because it seems pretty good and pretty important, and it's nice to have everyone agree on some particular thing to shoot at, but that doesn't mean it's really the best thing to shoot at.
All right, let's thank John once again.
Thanks. Thanks.